Sorry for the delay. I'm going to try to make it as quick as possible so we don't miss lunch. My name is Mariona Vila. Some of you may know me already. And I'm going to present a test assembly design problem and some metaheuristic and heuristic algorithms to solve it. So the problem we're concerned with is actually a bin packing problem, a minimax bin packing problem with bin size constraints. That's a bit of a tongue twister. And the problem has the following structure. We have a series of items that are initially distributed in a series of sets. And each one of the items has a specific weight. And we want to distribute them into another series of groups such that each one of the groups contains one item from each one of the initial sets. This can be assimilated to a test splitting problem or a test design problem, because we can imagine that the items are questions to evaluate people on some kind of criteria, and we have them initially divided in sets that can be, according to subject, according to difficulty, anything, and the weights are usually related to the difficulty of the question. So, for example, how many people or or what a percentage of people were able to answer correctly to this question. And we want to create tests, different tests, that contain one question from each one of the subjects or each one of the sets. And our, for example, this would be a possible solution. And our objective is to make them as even as possible in terms of difficulty. So we want to minimize the maximum difficulty of any of the tests, because we all know how students are, and we want to make them complain as little as possible. So for example, in the example that we have here, if we exchange questions D and C, we obtain a better solution for this problem. Yeah? In this case, the obvious optimum. But so this is the mathematical formulation of the problem. I'm going to skip it quickly because it's just minimizing the maximum weight of all the final groups. We need to assign all the questions, and in each questionnaire, I have to have one question from each one of the sets, and the variables are binary. As for the state of the art, this problem was initially formulated 2 years ago in a paper by Brusco et al. And they presented a formulation for the problem, a simulated annealing procedure for its solution, and a discussion on the complexity of some cases. They discussed that maybe the cases where we have only 2 questions per set was solvable in polynomial time. This problem is used, aside from in education, it also appears in the area of psychology. And it's also related to other cardinality constraint bin packing problems and multiprocessor scheduling problems. About the complexity of this problem, well, as I said, there was already some discussion about maybe some specific case of this problem being solvable in polynomial time. But as we can see, even the most simple form of this problem, which is the problem in which we have only two questions per set, can be the two-partition problem can be reduced to this case. The two-partition problem, I have a set of items, and I want to partition them into 2 subsets, such that the sum of the weights in both subsets are equal. So if I take all these items and I distribute them into sets, and I fill the sets with virtual items that have a weight of 0, this is exactly the problem, my problem, the test splitting problem. And it can only have a solution with an optimal value of sum of the weights divided by 2/2 if the solution to the two-partition instance was yes. So as the two-partition problem is known to be NP-complete, our problem is NP-hard even in this particular case. And a very similar reduction can be done for the general form of the problem to a three-partition problem. And as the three-partition problem is known to be NP-complete in a strong sense, then our problem is NP-hard in a strong sense. So given that this is an NP-hard problem, when when we started thinking of ways to solve this, the first idea is a greedy heuristic. Very simple greedy heuristic, has a complexity of t times b log b, and it has a performance guarantee of the greatest difference between any items on a given set. So in this case, the greatest difference between items in one single set is 4, which is in set 3. We can see that the maximum difference is 5 minus 1, 4. So any solution that we obtain with this heuristic will be at most 4 units from the optimum. And the working of this heuristic is very simple. The first we select an ordering of the sets, because the solution obtained may vary if we select a different ordering. But in this case, to make it simple, we'll just go 1, 2, 3, 4, 5. So the first set, the items are assigned at random to the final groups. Then set 2, we take the partially filled questionnaires and we order them in a non-increasing order, so 3, 2, 2, 1, and then the questions in a non-decreasing order, so 2, 2, 3, 4. And then we assign them the ith question to the ith questionnaire. And we keep doing this for every set until we get the final solution, which you can't see it, but it is an optimal solution because the weights are 15, 14, 15, 15. So as I said, different orderings of the sets may give me different solutions, so it's a good idea to try with different orderings. Now let's go for something a little more complicated and bound to give us a better solution. A hybrid genetic algorithm that uses optimization subproblem. I'm going to explain this fairly fast because it's a very simple genetic algorithm. The only interesting part is the crossover. That's where the magic happens. So the encoding of this, each individual is encoded as a matrix, as you see here. So if I have a solution such as this one, where I have, I don't know, the first question from set 1 assigned to questionnaire A, I have an A in the first column and first row. Yeah, I mean, it's very simple. And the fitness of each individual, it's just the inverse of the objective function. So in this case, 1/32. The initialization, the initial population is created using the greedy heuristic that I just explained with different random orderings of the sets. And also a local search is applied to the individuals. And the local search is very easy. We just select a set at random, for example, set 3. We deassign all the questions from set 3 or set 4. I don't know which one it is. Set 4, yeah. We deassign all of them, and then we reassign them using the heuristic rule that we used before. And the solution may improve. Now, about the genetic operators, selection and replacement, it's a simple standard tournament selection. We don't use mutation. We're trying to intensify the search, so we don't use mutation. And the crossover, as I said, this is the fun part of the, well, it depends on what you do for fun, but it's a fun part of the algorithm. What we do is an endpoint crossover with an optimization subproblem. So I'm going to explain this with an example. Suppose we have these two individuals as the parents, any two individuals, yeah? And we have one single cut in set 3. So the information of the first parent, we will use the information up to set 3 from the first parent and the information from sets 4 and 5 from the second parent. And what we do is we take everything that's assigned to questionnaire 1, everything that's assigned to questionnaire A in the first parent, and we transform that into another question. And the weight of that question 1 prime, will be the sum of these weights. So in this case, 15. Yeah? And we do the same for questionnaire B, the same with questionnaire C. And now we have another instance in which set 1 has a question 1 that corresponds to everything assigned to questionnaire A, a question 2 that corresponds to everything assigned to questionnaire B, and a question 3, etc. And a second set that corresponds to the same information, but from parent number 2. So we have a new instance that's much smaller than the instance we had initially, and we can solve this instance to optimality with Cplex in a reasonable amount of time. I mean, in this case, it's obviously very simple because it's just 1 point crossover, and it's a very small example. But even with a big example, this would be fairly simple to solve with Cplex. So we obtain the optimal solution, and then we deaggregate the solution obtained to get our new individual. We just see where those questions were coming from the original parents, and deaggregate the solution. So we use the instance set proposed in the same paper and the simulated annealing procedure for comparison purposes with a time limit of 10 minutes per algorithm. And the solutions, you can see them right here. It seems that our algorithm works very well for big instances, but not for the biggest instances, and does a fairly good job, or at least comparable to the simulated annealing procedure for the smallest instances of the set. So we proposed even another solution procedure, a variable neighborhood search, in which we scan several solution neighborhoods, all of them based on the heuristic rule that the greedy heuristic used, the greedy heuristic that I explained uses. So the first neighborhood is just, remember the local search from the genetic algorithm? It's very similar. We just select sets, in this case not at random, but in an order. We select one set, we deassign everything in that set, and we reassign it again using the heuristic rule. And we do that for all the sets. And if we obtain a better solution, we save it, we keep it. Okay. Then for the second neighborhood, we do something very similar, but instead of deassigning one set and reassigning it, we deassign and reassign groups of sets. For example, set 1, set 2, I separate that. I separate this set, and I deassign these 2 sets. But as let's say, as one same thing. We don't reassign them one by one. We reassign them together, and we reassign them using the heuristic rule. In this case, we have switched these 2, and we do this for every group of sets, for every possible combination of group of sets. Yeah. No, you end up using all of them. So you, exactly, 2 by 2, and then 3, and then 4, until you have done every possible combination. Yeah. Well, yeah. Not every possible, because you have already. Oh, yes. She asked, how do we select these 2 sets to deassign? And I said that it's not actually like selected. We just do every possible combination. Not the ones with 1, because we have already done those, and obviously not the number of questions minus 1, because we've already done those as well. But this is why, yeah, sorry, I mean, I'm trying to go quickly, and that's maybe why I didn't explain exactly everything, but yeah. And then the third neighborhood, what we do is we select the questionnaire with the most weight and any other questionnaire, and we deassigned all the questions from those two questionnaires. So for example, in this case, the questionnaire with the most weight is this one, and for example, we select this other one. And we deassign the questions from these two questionnaires, and we reassign them again, using the heuristic rule again. But in this case, instead of solving, of course, this is easy because it's just 3 questionnaires in the end, but if you have like, I don't know, 50 questionnaires, reassigning 2, it's actually very easy with the heuristic, and it always, for 2 questionnaires, the greedy heuristic always gives the optimum. So at least you know that these 2 questionnaires are optimally assigned. The rest is a question that is still pending, but at least you know that those 2 are optimally assigned. And the search scheme works as follows. We first apply the greedy heuristic. The first solution, we obtain it using the ordering of the set from most difference between elements of the set to least difference. And then once we have this first solution, we start scanning neighborhood 1. Then if the solution improves, we go to neighborhood 2. If the solution improves, instead of going to neighborhood 3, we go to neighborhood 1 with our new solution, and so on. And if we get to neighborhood 3 without the solution improving, and the solution improves, we go back to neighborhood 1. This is simply because neighborhood 1 is much more computationally easy to calculate. So, and neighborhood 3 is the most expensive computationally, so this is why we did it. And if we get to the end of neighborhood 3 with no improvement on the solution, there's a shaking procedure. This is just, we get a random order of the sets, and we obtain a new solution. We obtain a new solution, and we go back to the beginning. Yep. And the results for this, again, we use the same instances from Brusco et al. We compare with the simulated annealing procedure. And we see that in this case, we obtain very good solutions for the small instances, which was a drawback that the genetic algorithm had. And we also obtain very good solutions for the big ones, except for the very, very, very big ones, but that's normal, that's usual. We know the quantity of optimal solutions because we compared with a trivial lower bound. Just to say, just so you have an idea on how fast this algorithm worked, all the best solutions were found in 1.1 seconds. And for every set of instances, the optimality gaps were smaller for our procedure than for the simulated annealing algorithm. To conclude, I've discussed the complexity of this problem, and given that it was an NP-hard problem, we proposed some metaheuristics and heuristic algorithm for its resolution, a greedy heuristic with a performance guarantee, a hybrid genetic algorithm that uses an optimization subproblem, a variable neighborhood search that is based on the heuristic rules presented in the greedy heuristic, and both the genetic algorithm and the variable neighborhood search obtain very good solutions in small running times, especially the variable neighborhood search that works very, very well, and outperform the existing metaheuristic for the problem. Thank you very much for your attention. If you have any questions, this is your time to ask me. Y no sé si.